You think you know what an atom looks like. You've seen the pictures. A tiny nucleus in the center, like a ball. Electrons orbiting around it, like planets circling the sun. Clean, simple, easy to draw. That picture is in every textbook. Every science museum has a model hanging from the ceiling. Little balls on wires spinning in neat circles. But here's the problem. That picture is wrong. Not a little wrong, not close enough for government work wrong, completely, utterly, fundamentally wrong, in a way that should make you question everything else you think you learned in school. The atom is not a miniature solar system. Electrons are not little planets. And if you try to understand what's actually going on inside an atom using that picture, you're going to fail. You're going to get confused. You're going to ask questions that don't have answers because the questions themselves are based on a lie. So let me tell you what's really inside an atom. And I'm warning you now, you're not going to like it. Because what's actually there is so strange, so contrary to common sense, that your brain is going to fight me every step of the way. Let's start with the simplest atom, hydrogen. One proton, one electron. That's it. The atom everyone uses to explain things because it's supposed to be simple. You imagine the proton sitting in the middle, a little ball maybe 10 to the minus 15 meters across. And the electron is somewhere out there, maybe 10 to the minus 10 meters away, orbiting around it. First question, where exactly is the electron? You want to say, well, it's over there, on the left side of the atom right now, moving in a circle. Wrong. The electron is not over there. The electron doesn't have a definite position. Not because we can't measure it precisely. Not because our instruments aren't good enough. Because the electron itself doesn't have a definite position until you measure it. This is not philosophy. This is not interpretation. This is what the math says. This is what experiments confirm over and over and over again. The electron exists in a state we call a superposition. It's not here or there, it's here and there, simultaneously, in multiple places at once. The electron is smeared out in a cloud of probability around the nucleus. Now you're thinking, okay, fine, it's a cloud. So the electron is spread out like butter on toast, thinly distributed over a region of space. No, that's still wrong. The electron is not spread out. The electron is a point particle when you measure it. But before you measure it, it doesn't have a position. What's spread out is the probability of finding it in different locations. There's a function called the wave function that tells you where you're likely to find the electron if you look. In some places, the wave function is big, high probability. In other places, it's small, low probability. In some places, it's zero. You will never, ever find the electron there. But here's the thing that breaks your brain. Before you look, the electron isn't hiding in one of those high probability spots. It's not secretly over there and you just don't know where. It genuinely doesn't have a location. The wave function is the electron. That's all there is. Now let's talk about orbits, because this is where the solar system picture really falls apart. You imagine the electron going around the nucleus in a nice circular path, round and round like a racetrack. Maybe it's going fast, maybe it's going slow, but it's definitely going somewhere. Wrong again. First problem. If an electron were actually orbiting like that, it would be accelerating. Anything moving in a circle is accelerating, even if its speed is constant, because its direction is changing. And accelerating charged particles radiate energy. They emit light. That's basic electromagnetism. We can measure it. It happens. So if the electron were really orbiting, it would be constantly losing energy, radiating it away as light. And as it loses energy, the orbit would shrink. The electron would spiral inward, closer and closer to the nucleus, faster and faster, until crash, it hits the proton and the atom collapses. How long would this take? Do the calculation. It takes about 10 to the minus 11 seconds, 100 trillionth of a second. Every atom in the universe should collapse instantly. Obviously, that doesn't happen. Atoms are stable. They don't collapse. So the electron can't be orbiting. Okay, you say. So maybe it's not orbiting in a circle. Maybe it's just sitting there, stationary, held in place by the electric attraction to the nucleus. Also wrong. Because if the electron was sitting still, we would know both its position and its momentum exactly. Position, right there. Momentum, 0. And quantum mechanics says you can't know both of those things exactly at the same time. That's the Heisenberg uncertainty principle. It's not a limitation of measurement. It's a fundamental property of nature. If you try to pin down the electron's position, its momentum becomes uncertain. If you try to pin down its momentum, its position becomes uncertain. You can't have both. So the electron is not orbiting, and it's not sitting still. What's it doing? It's not doing anything. It just is. It exists as a wave function, a mathematical description of probabilities. And that wave function has certain allowed shapes and energies. We call these shapes orbitals. An orbital is not a path. It's not a trajectory. It's a region of space where the electron is likely to be found, described by the wave function. The simplest orbital, the ground state of hydrogen, is spherically symmetric. The probability cloud is highest right at the nucleus and falls off gradually as you move away. There's no orbit, no path, just a fuzzy cloud of might be here. Higher energy orbitals have stranger shapes. Some look like dumbbells. Some look like donuts. Some have multiple lobes. These aren't physical objects. They're probability distributions, maps of where you might find the electron if you look. And here's the really weird part. The electron doesn't gradually transition from one orbital to another. It doesn't slide smoothly from the ground state to an excited state. It jumps instantaneously. We call it a quantum leap. One moment the electron's wave function is in the shape of the lower orbital. The next moment it's in the shape of the higher orbital. There's no in-between, no smooth transition. It doesn't travel through the space separating the two orbitals. It just jumps. How? We don't know. The math describes it. The experiments confirm it. But there's no mechanism, no explanation for how the electron gets from here to there without passing through the middle. It just does. Now let's talk about what the electron actually is, because this is where things get really disturbing. You think of the electron as a little ball, a tiny sphere with some mass and some charge. Maybe it's very small, but it's still a thing, an object, a particle. Except when we do experiments, we find that the electron also behaves like a wave. It can interfere with itself. It can diffract around obstacles. It can spread out and recombine. All the things waves do. So which is it? Particle or wave? Neither. The electron is not a particle. It's not a wave. It's a quantum object. Something that doesn't have a classical analogy. Something that exhibits particle-like behavior in some experiments and wave-like behavior in others, but is fundamentally neither. When you're not looking at it, it's described by a wave function. That wave function evolves smoothly, spreading out, interfering with itself, doing all the things waves do. But when you measure the electron, when you actually detect it, you always find a localized particle, a dot on a screen, a click in a detector, never a smeared out wave. The act of measurement collapses the wave function. The spread out probability cloud instantly becomes a definite outcome. Here, not there. One spot, localized. And nobody knows how this happens. Nobody knows what counts as a measurement. Nobody knows where the wave function goes when it collapses. This is called the measurement problem, and it's been bothering physicists for nearly a century. There are interpretations, many worlds, pilot waves, objective collapse, but they're interpretations. The math works, the predictions match experiments, but we don't have a clear picture of what's actually happening. Let's make it worse. Let's add more electrons. Helium has 2 electrons. Lithium has 3. Carbon has 6. Iron has 26. These electrons are all orbiting. No, wait, not orbiting. They're all existing simultaneously as wave functions around the nucleus. But here's the thing. The electrons are identical. Absolutely, perfectly, fundamentally identical. There's no way to tell them apart. Not because they look the same, not because they're very similar, because they are the same. Electron number 1 and electron number 2 are not 2 different things that happen to have the same properties. They're the same thing appearing in 2 places. This has consequences. If you swap 2 electrons, the wave function of the entire system changes sign. It picks up a negative factor. This isn't a detail. This is fundamental. It's called the Pauli exclusion principle, and it's the reason matter is solid, the reason you don't fall through the floor, the reason atoms have structure and chemistry works and life is possible. No 2 electrons can occupy the same quantum state. If one electron is in a particular orbital with a particular spin, no other electron can be in that exact same state. They have to stack up, filling different orbitals, building the structure we call the periodic table. Without this rule, all electrons would collapse into the lowest energy state. Every atom would be chemically identical. There would be no complexity, no molecules, no chemistry, no you. But why? Why does swapping identical particles change the sign of the wave function? We don't know. It's just the rule we discovered. The math works. The experiments agree, but there's no deeper explanation. Now let's talk about the nucleus, because you probably think that part is simple. A bunch of protons and neutrons packed together. Little balls stuck to each other. Wrong again. Protons and neutrons are not fundamental. They're made of quarks. 3 quarks each. Up quarks, down quarks, held together by the strong nuclear force, mediated by particles called gluons. But the quarks don't sit still inside the proton. They're quantum fields, fluctuating, interacting, constantly exchanging gluons. The proton doesn't contain 3 quarks the way a bag contains marbles. The proton is a bound state of the quark field, a stable pattern of oscillation. And here's the really strange part. Most of the mass of the proton doesn't come from the quarks themselves. Quarks are nearly massless. Most of the mass comes from the energy of the gluon field holding the quarks together. Energy equals mass. So when you ask, what's inside a proton? The answer is energy. Bound field energy. Not stuff, not particles. Energy arranged in a stable pattern. And the protons and neutrons in the nucleus, they're held together by the residual strong force. They're not touching. They're not glued together. They're trapped in a potential well created by the exchange of particles called pions. But pions are also made of quarks. It's quantum fields all the way down. So let's step back and ask the question again. What's really inside an atom? Not particles, not little balls, not orbits, not stuff. What's inside an atom is fields, quantum fields, the electron field, the quark field, the gluon field, the electromagnetic field. These fields fill all of space. They're everywhere, always. When we say there's an electron in an atom, we mean the electron field has an excitation localized near the nucleus. The atom is not a thing, it's a pattern, a stable configuration of field excitations held together by forces that are themselves carried by other field excitations. There are no solid objects at the bottom. There's no stuff. There's only fields. And the fields are just mathematical objects that assign numbers to every point in space and time. Numbers that evolve according to differential equations. Numbers that sometimes produce localized excitations we call particles. You don't like this. I can see it. You want there to be something real at the bottom, something solid, something you can point to and say, that's what it's made of. But there isn't. There's just math, equations, symmetries, conservation laws, and somehow, miraculously, that math produces the appearance of solid objects, tables, chairs, your body. All of it is patterns in quantum fields, held together by forces, stabilized by exclusion principles, flickering in and out of existence trillions of times per second. Here's another thing that's going to bother you. The atom is mostly empty space. You've probably heard this before, but that's wrong too. Because empty space doesn't mean nothing. The quantum fields are still there. Virtual particles are popping in and out of existence. The vacuum is seething with activity. And the electron's wave function fills the entire atomic volume. The electron is there in the sense that its probability amplitude is non-zero throughout the atom. When you push on a table, you're not feeling particles colliding. You're feeling the electromagnetic repulsion between electron clouds, field configurations resisting overlap, the Pauli exclusion principle preventing electrons from occupying the same state. It feels solid because the forces are strong, but there's no actual contact, no touching, just fields pushing against fields. Let's talk about size, because this is where your intuition completely fails. The nucleus is 100,000 times smaller than the atom. If you scaled the nucleus up to the size of a marble, the atom would be the size of a football stadium. But here's the thing. The electron itself, as far as we can tell, has no size. It's a point particle. Every experiment has come back with a result consistent with 0. So you have a point particle with no size, somehow occupying a volume 10 to the minus 10 meters across. Does that make sense? No, of course not. But that's what the experiments tell us. Nature doesn't care whether it makes sense to you. Now let's make it even worse. Let's talk about spin. Electrons have a property called spin. It acts like angular momentum, like the electron is rotating. But the electron is not spinning. It can't be spinning because it's a point particle. A point has no extent, so it can't rotate. There's nothing there to spin, and yet the electron has angular momentum. Intrinsic angular momentum that doesn't come from motion. It's just a property the electron has, like charge or mass. We call it spin because it has the mathematical properties of angular momentum, but it's not actual rotation. This spin is quantized. Spin 1/2. You can measure it along any axis, and you'll always get one of two answers, up or down. Never anything in between. But before you measure it, the spin doesn't have a definite direction. It's in a superposition. And the moment you measure it along one axis, it becomes uncertain along perpendicular axes. Why? We don't know. It's just how spin works. Nothing in your everyday experience behaves this way. Energy levels in an atom are quantized. The electron can only have certain specific energies, not any old energy. Specific, discrete values. Why? Because the wave function has to fit around the nucleus. It's like a vibrating string. A string can only vibrate at certain frequencies, the fundamental and the harmonics. Same with the electron's wave function. Only certain wavelengths are allowed. And since energy is related to wavelength, only certain energies are allowed. When the electron transitions from one state to another, it emits or absorbs a photon with exactly the energy difference between the two levels. This is why atoms emit light at specific wavelengths. Why hydrogen has its characteristic red line, its blue line. Each line corresponds to a specific jump between energy levels. We can measure these wavelengths to extraordinary precision. We can predict them using quantum mechanics to extraordinary precision. They match to 10, 12, 14 decimal places. The theory works. But why are energy levels quantized? The math tells us. The experiments confirm it, but there's no deeper reason. Now let's talk about what happens when you try to look inside the atom. You can't use visible light because the wavelength of visible light is bigger than the atom. You need something with a shorter wavelength, higher energy. But here's the problem. The moment you use high-energy probes to look at the electron, you disturb it. You knock it out of its state. You change what you're trying to measure. This isn't a technical limitation. It's fundamental. To see something small, you need short wavelength light. Short wavelength means high energy. High energy means large disturbance. You can't avoid it. The act of measurement changes the system. There's no such thing as a passive observation at the quantum level. This is why we can't say where the electron is before we measure it. Not because it's hiding, but because the property of being in a definite location doesn't exist until we perform a measurement that creates that property. Before measurement, the electron is described by a wave function, a superposition of possibilities. After measurement, the electron is in a definite state, one of those possibilities. The measurement doesn't reveal a pre-existing reality. It creates a definite reality from a fuzzy one. So what's really inside an atom? Not little balls, not orbits, not stuff, not even particles in the way you think of particles. What's inside an atom is a mathematical structure, a wave function, a solution to the Schrödinger equation, a pattern of probability amplitudes that tells you what you'll find if you look, but doesn't describe a definite reality when you're not looking. The atom is a quantum system, and quantum systems don't behave like anything in your everyday experience. They exist in superpositions. They have properties that are fundamentally uncertain. They defy visualization. You can't picture what's inside an atom because there's nothing to picture. The wave function is not a physical wave in space. It's a function in an abstract mathematical space called Hilbert space. It's a list of complex numbers that encode probabilities. It's information, not substance. And yet, from this abstract mathematical structure, the entire physical world emerges. Chemistry, biology, consciousness, all of it built from patterns in quantum fields, governed by equations, following rules that make no intuitive sense, but work with astonishing precision. This is what's really inside an atom. Not particles, not stuff, but math. Pure, abstract, beautiful, incomprehensible math. And if that doesn't satisfy you, if you still want there to be something more, something solid and real at the bottom of it all, well, I'm sorry. But the universe doesn't care what you want. It is what it is. And what it is far stranger than you ever imagined.